All right, so here's a second mixing problem. And what makes this different than the problem we did last time is that the rate of fluid coming in, 2 gallons per minute, is different than the rate coming out, 3 gallons per minute. Right? So that's going to change things slightly from what we did before, but our approach is the same. We have our dependent variable, A of t, which is the amount of salt in the tank at time t, the amount in pounds at time t. And we set up a differential equation. We can't write A of t directly as a function. We don't know what that function would look like, but we can think about rates. So A prime is going to be the rate of salt in minus the rate of salt out. So at what rate is salt entering this tank? Well, we have 3 pounds per gallon, or 2 gallons per minute, times 3 pounds per gallon. The gallons cancel, and we have pounds per minute, 6 pounds per minute. So that's a rate of salt in, 6 pounds of salt per minute, minus the rate out. Now the rate out we have, we're losing 3 gallons per minute, but at what concentration, right? What's the concentration of pounds per gallon that's being drained? That concentration is going to be the total amount of salt in the tank, which is A, divided by the volume of liquid in the tank. So how do we do that? So let's multiply the 2 and the 3 is 6, minus 3 times A. The volume of liquid in the tank, well, it starts with 200 gallons, right? And then we have 2 gallons per minute coming in and 3 gallons per minute coming out. That means we're losing a net of 1 gallon per minute. So we're losing 1 gallon per minute. So the volume is not 200, but 200 minus 1 times t. 1 gallon per minute times the number of minutes, 1 times t. We could make that very explicit. That's 1 gallon per minute, and that's the number of minutes. So we multiply that together. That's the how much volume we're losing off of that 200. And so we end up with our differential equation, A prime equals 6 minus 3A over 200 minus T. And we have A of 0 is 10 pounds. There are 10 pounds initially. So that's our initial value problem. That is a first order, linear, non-constant coefficient differential equation, non-constant coefficient because the coefficient on A depends on T. It's not a constant. And so we would have to solve this with the method of integrating factors and not with muck because it's non-constant coefficient. But that's how we account for this if the rates are different, the rate in or out. What it's going to do is it's going to make the volume a variable, right? The volume is going to be changing in this process. If the rate in is lower than the rate out, then that's going to be a positive change. Instead of a 200 minus t, it could be a 200 plus something times t. And we look at that net difference of how many gallons we're either gaining or losing per minute. So that's it. There we go. That's a modification on our mixing problem.